Good afternoon. It is 1:30 in Philadelphia, and welcome to Thermal Live 2016. I'm Graham Kilshaw with Electronics Cooling Magazine, and this presentation is brought to you by Henkel Electronic Materials. The title of the presentation is Novel Thermally Conductive Low Pressure Overfold Materials as a Solution for Thermal Management. And your speaker this afternoon is Art Ackerman. Art is the Global Product Manager for Circuit Board Protection at Henkel, and he's speaking to us this afternoon from Irvine, California. Good afternoon, Art.
Thank you, Graham. Thank you, everyone, for joining. Again, my name is Art Ackerman, and I do appreciate your time today to discuss the thermally conductive overmold materials that we've introduced into one of our product portfolios here at Henkel Electronics. Quick background on me. I have a chemical engineering degree, been in applications and tech services for over 10 years, and now support the product line as a marketing function.
And we're also joined by MP Divakar, who's the Senior Technical Editor for Electronics Cooling Magazine. Good afternoon, MP.
Hi, good morning and good afternoon, and I would say, a good day to our audience worldwide. I'm joining you guys from Silicon Valley, California.
MP is going to be our master of ceremonies for the Q&A portion of this presentation. The presentation from Art will last about 35 minutes, and then we'll have about 15 minutes available for Q&A. If you do have questions you'd like to submit during the presentation, simply use the Q&A box located in the bottom left corner of your screen. Submit the questions this way. At any time during the presentation, we'll collect them and we'll do our best to answer as many as possible at the end of Art's presentation. If you have any technical issues during the presentation, most of the common issues can be solved by clicking on the yellow tab at the bottom of the screen. One of the interesting features of this particular webinar platform is that you can chat with other audience members. If you click the group chat button at the bottom of your screen, you can ask questions and interact with the other people attending today. And we have a wide variety of people attending this presentation by Henkel, including folks from Global Foundries, Teledyne, Altera, and even live somebody on from Hong Kong Polytechnic. Wherever you are in the world, welcome to you this afternoon. There are two more interesting links you may want to make use of during the presentation. At the bottom of your screen, you'll see one link shaped like a chain. This will take you to the Thermal Live website to register for the remaining presentations. And the second link takes you directly to the Henkel Electronic Materials website. I already see a couple of questions, people asking about when can we get the slides and the video. The slides from Art's presentation will be available to you in about 24 to 48 hours from now. You'll automatically receive an email when they're ready to access. And the video of this presentation will be available within an hour to 2 hours after the presentation. So no need to email us, just watch your inbox. And with that, I'm going to hand over to Art to begin this interesting presentation. Art, over to you.
Thank you again. Without further ado, let's go ahead and begin. So in today's presentation, we'll cover three broad areas: Henkel Electronics portfolio of solutions, the Technomelt overview, which talks more specifically about this particular product technology, and finally the thermally conductive solution, which is the novel concept in which we've introduced a new material for encapsulation purposes. At Henkel Electronics, the way that we approach encapsulation or circuit board protection is a full portfolio of solutions with traditional potting, conformal coating, and sealing technologies at our disposal. Additionally, we have a material called low-pressure molding, or Technomelt, which serves fundamentally to replace or as an alternative solution to many potting applications. This is a thermoplastic material that can be used via low-pressure molding to be compatible with sensitive electronic components and devices on boards. In each, we offer a unique value proposition of the fundamental performance of the materials to allow for any application or technology to make use of the necessary material sets. In the end, we strive to deliver high performance reliability for the electronics industry via these solutions. Again, Hinkle approaches the electronic materials market by providing a value proposition to its customers, protecting electronics from the impact of moisture, high temperature performance, electrical insulation and of components and circuits, and design for manufacturing, which is where the Technomelt materials fall into play specifically. In addition, we like to think of ourselves as developing solutions to meet the challenges of our customers' unique needs, in particular, the thermal management requirements. Many other traditional technologies don't go far enough to support the thermal requirements. Therefore, a secondary material may be needed, applied after the fact, after electronic component itself is encapsulated or molded. Looking more closely at the Technomelt solution, it's important to understand what this material really is and how it behaves. I mentioned before that Technomelt is a hot melt polyamide material designed for electronic components. It's a thermoplastic material, so it's different than your traditional epoxies or acrylic resins where there's actually a polymerization that occurs during a cure step. In this case, the material is processed at relatively low temperatures. It's melted, molded onto the board at relatively low pressures, much lower than what you would see in plastic injection molding, and once cooled, provides a complete encapsulation around sensitive electronics. And it's really the combination of this low temperature and this low pressure that allow it to be compatible with electronic components. The benefits include complete watertight encapsulation. So once you've molded a piece of electronics with this material, it's impervious to moisture ingress. Temperature and solvent resistance. Many of these materials were originally designed for the automotive market, where they were exposed to very harsh environments related to ATF, for instance, automotive transmission fluids, and things like that, exposing during environment in situ. The materials themselves are inherently UL rated at 94 V0. The process itself has a very short cycle time, and we'll discuss this in more detail later, but what you're probably familiar with a potting material that's epoxy-based, for instance, you either have a long room temperature cure or you have a shorter elevated temperature cure, but still that's a matter of 30 minutes to 60 minutes, for instance, whereas this cycle time is the matter of minute to minutes. It's inherently a green technology, meaning there's no VOCs and minimal waste. Since, again, it's a thermoplastic, there's no cure reaction that occurs, and there's no volatiles given off during its cooling process. We look at this material as being an option in our toolbox to lend in lowering the total cost of ownership and use, looking at it from an overall process standpoint. Two images on the right you see are an optically clear material that molds around components where you're able to shine through with very high transmittance rates. And the black material on the bottom is a matte material that also molds around LED boards to ensure encapsulation for outdoor applications. A little more detail about the process for low pressure molding in Technomelt solutions. Really, this becomes a simplified manufacturing process. You're familiar with traditional potting applications, for instance. You need a case of some sort. You place the electronics in a case. You then fill that case with the amount of potting material that you need. Then you go to an oven step to cure. And from there, you let the material settle, cure, and then you're ready to test. With low pressure molding solutions, you place the electronics in and move to a piece of molding equipment. At low pressures and low temperatures, the material is injected into the mold set, allowed to cool within about a minute to two, and then the part is ready for test then. There's no subsequent curing step. So what this does is it reduces the number of manufacturing steps, reduces the number of pieces of equipment and the operations footprint in total, allows for fewer machines in the manufacturing line, reduces that cycle time per part, and since it's a very low viscosity material, it allows for really low injection pressures, so it can be used in collaboration with components that are soldered onto a board, for instance, BGA components or traditional SMT or SMT mounted components. The depiction here shows the three simple steps that we like to focus on for electronics molding. Placing a piece of electronics, so a fully populated board, for instance, into a custom designed mold set closing that mold set, injecting the Technomelt material, again at relatively low pressures and low temperatures, and then waiting a minute to two for it to set or to cool, pulling that piece of electronics out, and it's now molded and ready for test. Again, you're avoiding that long cure cycle at the on the back end, and also reducing the overall amount of material used because a mold set itself is custom designed for the part. The mold tools themselves, if you're familiar with injection plastic molding, for instance, you would probably have used a stainless steel mold set. In this case, are aluminum. Or most often, they're usually aluminum. They're very easy to mill, drill, and etch. They provide good release of the molded parts, so you don't have the same issues you would have if you were doing plastic injection molding. You can provide steel inserts are recommended in contact areas with harder metal parts to prolong the life of these mold sets. But it does offer very long life, and since the Technomelt material is non-abrasive as a resin and non-corrosive, these mold sets last for a significantly longer period of time than what you may be used to. I mentioned before the process conditions utilized in low-pressure molding applications. If you think about traditional plastic injection molding, or even molding with traditional potting materials, the injection pressure itself is relatively high. For low-pressure molding, since you're at, and also the temperature itself is rather high, sometimes above the liquidus of the solder joints with which components are laid down. In the case of low-pressure molding, the time and temperature are relatively lower than that injection plastic molding, making it suitable for sensitive electronic components. Also, the process time is significantly shorter, so the actual temperature that a solder joint, for instance, would see is only observed for a very short period of time, meaning there's very marginal impact to anything related to the solder joint reliability. The products themselves have been optimized to meet the needs of the electronics industry. They're lightweight materials, so the density of unfilled materials is less than 1. They have excellent adhesion to multiple surfaces. They are watertight encapsulation materials, are designed to be watertight encapsulation after molding. Provide high temperature, shock, and environmental resistance, as well as solvent resistance. I mentioned before that there's no cure, as this is a true thermoplastic material, so there's no byproducts given off. It's a very compliant material, which is suitable for that sensitive electronic component, which we get questions on quite often, given that it is a thermoplastic and people are very familiar with plastic materials itself. Quick general glimpse of the material properties itself. The materials are temperature resistant. They have, for short-term exposure, up to about 185 degrees C. Again, the portfolio is tailored to offer solutions across the gambit, but typically we see the maximum temperature exposure at short terms to be 185. They're very flexible materials. Their elongation and rupture can be up to 800%, so very similar to the plastics you are familiar with. From a cold temperature flexibility, meaning how well does it do at cold temperatures, we can go all the way down to -50 in terms of a mandrel bend or 180-degree bend before cracking. The materials have good chemical resistance related to automotive fluids for short-term exposure, and generally good chemical resistance related to non-polar liquids like oil, and those can be done in long-term harsh environments. It is a plastic, again, so it does absorb moisture, 0.2 to 2%, 24 hours at 22 degrees C. However, it reaches a saturation point, whereas no more moisture would absorb into the material, and the migration into the electronics is null. I mentioned before that there are flame retardant properties. The materials, many of them are UL listed at 94V0, and some are even RTI certified. A quick example of some of our traditional products, going from very general materials to high strength and high hardness materials, those that have excellent adhesion and flexibility, and even some designed for high working temp. We also have materials designed for with special considerations, such as RTI ratings and things of that nature. You'll notice the temperature windows for these, the operating temperature windows, vary from -40 up up to 100, even 130 to 140 degrees C for the general products in the portfolio. Many of the resins that we've selected are tailored specifically for different applications, so they provide a different set of properties. However, in the scheme of things, they're all simply resins. The chain lengths may be different, but they are unfilled polyamide thermoplastic resins, providing minimal functional benefit other than what the sealing capabilities or encapsulating capabilities are. But using these materials, you can leverage something related to the design itself of your application. So no longer are you bound by the traditional potting application, for instance. You can now use the mold set to combine these materials into the electronics market. Allows for improved design flexibility with precise design, allow for more space and flexibility within the final assembled products. Design capabilities beyond the fit, form, and function of the traditional materials. In the picture on the right, you can see where the material was molded around a handle. Traditional potting materials would not be able to do this, allowing for skylining and reduction of the overall weight of the unit. Also, there's an improved aesthetic appearance, and no additional housing is needed in many circumstances. The technical materials themselves are quite good in other areas as well, such as sustainability considerations. The waste is minimized through the process, and since it's a thermoplastic with no reaction, any runners or things like that can be conceivably reused. They are natural ingredients with no harmful fumes from the molding process. So if you've ever been in an injection plastic molding house, for instance, or even curing an acrylic material, for instance, there's an odor that's given off during those processes. With this, the odor is non-hazardous, if there is any odor, and the materials themselves, since they're derived by natural raw materials, continue to be very sustainable and very eco-friendly. So all are RoHS and REACH compliance. Materials themselves obviously have a long shelf life, considering they can stay at room temperature for prolonged periods of time, and are very flexible in terms of how you intend to use them. We look at quite often at total cost of ownership. In other words, not just recommending the material itself, but trying to, or a particular material itself, but trying to recommend the right material for the right application to meet the overall requirements of the application itself. From a cost-saving standpoint, we like to highlight the fact that these materials allow for fewer physical parts, reducing the number of items on the bill of materials, reduce shipping costs of final products, given that the materials can be used in less weight. So the configurations could be a thinner form factor. Overall, the reduced total cost of ownership, an increased throughput given that the materials don't require subsequent cure steps, relatively lower capital equipment costs versus some of the traditional molding equipment or even some of the traditional potting equipment itself. Your inventory and work in process is also reduced. And finally, lower labor costs, as these pieces of equipment and the molding process itself requires very little oversight and very little operator input to it. When you compare the traditional potting process flow itself to the low-pressure molding process, you see the number of steps are significantly reduced, and by that, the overall time per part is reduced as well. With the traditional potting process, you have a plastic housing of some sort that may need to be molded in a separate step. As parts needed to be assembled and placed into a configuration to go into that housing, you insert those electronics, possibly preheat the parts to allow the potting material to flow well and reduce the voids and bubbles, dispense the potting material, allow for a settle time or possibly do so under vacuum, and then move into either an oven cure or a prolonged room temperature cure, and finally your parts are ready for test. Whereas with the low-pressure molding process using these materials, you insert the parts, overmold with the low-pressure molding Technomold material, and then the parts are ready for test in a matter of minutes. The three main elements we look at are the process itself, the materials, and the equipment to compare with traditional processes and try to leverage this material's capabilities to offer a lower total cost of ownership. For process-wise, there's less manpower required per line. Material side, reduced material consumption per part. On the equipment side, fewer pieces in a smaller footprint. Now that we've laid the groundwork for what the Technomelt portfolio looks like and how these materials function, I wanted to talk more specifically about the thermally conductive solution that we've promoted today. This is really a first-of-its-kind type of material, adding a filler into a electronics-compatible, injectable hot melt polyamide resin. So this is a traditional thermoplastic hot melt adhesive, which is designed for encapsulating these sensitive electronics. We functionalized the performance of the material, to provide a bulk conductivity over half a watt-meter K. These materials, as a resin themselves, are typically 0.2 to 0.3 watts-meter K, meaning they're effectively insulating. There's no heat transfer through the encapsulant itself. The novel filler package we've developed allows for process and standard low-pressure molding equipment. In other words, it doesn't require significantly change to how the materials are applied today. The project goal we endeavored down to was to develop a higher thermally conductive material. As I mentioned before, with 0.2 watts-meter K, you really don't transfer much heat. The thermally conductive Technomelt allows heat transfer through that molded encapsulating layer. Our first generation material is over half a watt-meter K. It's actually measuring at about 0.6, 0.7. Our goal is to develop a material roadmap with materials up to 1.5 watt-meter K for more power electronics-centric type applications. In the depiction below, you have molded components that have been mounted onto a circuit board, and then they are molded with a layer of encapsulating material. And in this case, if this was done with a traditional hot melt polyamide resins, no heat would transfer through that layer. However, with the thermally conductive material, heat therefore can transfer out of the encapsulating layer instead of through the board or into some heat via that's been designed in. Brought a quick snapshot of traditional Technomelt materials versus the thermal materials. You'll notice the density itself is higher, and that's due to the filler addition. The break strength, though, and the elongation properties all maintain well enough to survive the environmental exposure that we would expect to see: thermal cycling, high temperature storage, stress itself. The material is relatively harder given that the filler has been introduced, but still provides a very good yield strength. And the modulus itself is increased, but not by more than not by a factor of 10, which is typically in the materials world where we start to consider fundamental differences between the behavior of materials. And the viscosity itself at melt temperature is less than 10,000 centipoise, which allows it to be moldable. And again, that main critical factor is that the material is now thermally conductive. So the functional benefit you're seeing from the encapsulation now is its thermal conductivity. Highlighting the performance of this material again, the TC50, or the thermally conductive Technomelt, allows for sealing of electronic components using the low-pressure molding technology. Thermal conductivity is greater than half watt, enables the heat dissipation through the encapsulating layer. We've done significant thermal modeling and in-package testing, which shows significant reduction of component operating temperatures. And we'll go into that in the next couple of slides. From a product standpoint, though, a technology standpoint, again, I talked about viscosity, hardness, elongation, and break strength previously. What we see is an operating temperature with minus 40 to about 150 degrees C. This material is going into RTI certification now. With that thermal conductivity, we expect good things for both those ratings to come out. In the two images below, you see a LED driver board being molded, or a mock-up of it being molded, and then placed into its frame. This is a thermal model developed internally here at Hinkle, where we looked at unfilled material at a 0.2 to 0.25 watt-meter K versus filled material at 0.5 watt-meter K. What we did is try to develop a part that we could use to test the actual difference between these two materials in terms of functional performance and measure its actual benefit for an application itself. So in the top of that depiction on the right, what you see is a power device mounted on a board and then molded with the Technomelt material. It's placed against a heat sink to direct the heat from that power device out into the material itself, and we've measured the performance or the temperature in this model in both situations. What we saw is about a 40 C reduction in the observed operating temperature between these two situations. So again, this power device is at the same power rating with the same current going through it and power dissipation. However, the material itself in the bottom picture is allowing for a more uniform distribution of the heat outside of the layer, or through the encapsulating layer away from the board. How does this work in, or how does this look in a more realistic setting? We took this IGBT, which you can see in the image on the right, and mounted that to a circuit board. After mounting to a circuit board, we then molded these parts. So we put them in a low-pressure molding tool in a mold set, injected the standard Technomelt around or into that tool set, and encapsulated the part, leaving just the pins themselves exposed. Those pins were then placed into a jig that was then powered up, or used to power up the device itself, and we were able to monitor the heat curve, or the cooling curve in this case, for that particular component. So the test setup used a sense current of 200 milliamps, heating current 36 amps, 20 seconds of heating, so we turned the heat on for 20 seconds, and then monitored for 2,000 seconds on the cooling curve. The analysis itself, or comparison, is performed off the cooling curve when the power reached 42 to 45 watts. So pretty high power for these devices themselves. What you see in the difference in these two curves is, one, the standard curve on the top, and two, the curve with the part molded with TC50, or the thermally conductive encapsulant, on the bottom. Again, this is a molded IGBT, so something that would have mold compound already around the device itself, mounted onto a PCB, so a green circuit board, and then molded over the top using the Technomelt materials. Again, we're comparing the standard material that's unfilled with a thermal conductivity of 0.2 watt meter K, and the thermally conductive material, TC50, with a thermal conductivity greater than a half watt meter K. And the image on the right is the output off the cooling curve, and you see the difference in those two curves equating to about 38 degrees C of the junction temperature measured. So the thermally conductive material allows for the heat to dissipate through the encapsulating layer, allowing that junction temperature to remain significantly cooler. We grabbed some images with an IR camera as well. These images were taken at some point, or at the same point, 15 seconds of heating at 45 watts and 35 seconds of cooling, so into that cooling curve itself. So after they heated up, we let them cool, and 35 seconds later captured an image. The crosshairs, the actual temperature is shown on the upper left at 61.9 degrees C for the thermally conductive material, and 86.6 degrees C for this PA670A, which is a traditional material with 0.2 watts meter K. So what you're seeing in this environment, you're seeing that the heat is dissipating more uniformly through the encapsulating layer, and also the exact point where we're measuring, the heat itself is not reaching the same level as with a insulating material, which is what you would expect to see. But just a visual representation to reinforce the previous slide, the data we received there. In this particular case, we've started to see interest from many different industries and applications. This particular one is a temperature sensor for an engine compartment. The function here, the heat is transferred from the connector through the molded material to the sensor inside. Traditionally, they would use a non-filled resin to mold these, and they get performance of a certain level. What they see here is, using the thermally conductive material, their sensing performance is actually significantly improved. So the test this material goes through after molding: high temperature storage, humidity testing, and vibration testing. The thermal conductivity allows for faster response time versus traditional materials, which improve the performance, which is driving the interest in material for this particular application. We have a variety of target market and applications that we find interesting for this material, both in LED electronics, for instance, driver boards, control units, and even ballast and fixturing. On the solar side, for inverters, power management electronics, and smart connectors. And on automotive electronics, power steering modules, inverter modules, battery cooling, and power management. Many of these are under investigation right now. We supply materials to quite a few applications in these areas in more of the traditional sense, from potting, conformal coatings, and sealing materials. And now we're introducing this as an option for those particular markets and applications to look at. One quick note about the material. I tend to get this question often: how is it packaged? The image you see is actually from one of our manufacturing sites. The material comes out as small pellets, small plastic pellets, if you will. Again, they're hot melt, thermoplastic, polyamide resins in a pellet form. Typically, in this case, a 1 gallon, 3 gallon can or pail, with additional options available for a much larger volume. Product name itself, Technomelt TC50. Tech data sheet is included here, and we have a contact name for our technical resource in the Americas. But we have technical engineering staff globally to support questions on these particular applications. I mentioned earlier on that we have a development roadmap that we continue to endeavor down, with the TC50 being the first material introduced here to meet the functional requirements of a material with greater than half a watt meter K in the molding and encapsulating line. We're targeting a 1.5 watt meter K material as well, and then also to continue to look at blending features, where I mentioned earlier some of our resins are UV stabilized or high temperature stabilized. We would introduce this functional benefit of the thermal performance to those as well. Brings us to the end of the presentation now. I wanted to sum up and conclude, reinforcing the fact that Hinko's low-pressure molding process using the Technomelt materials meet demands of the challenging electronics market. Again, these are low-pressure moldable and low-temperature and relatively low-pressure versus injection plastic molding. The materials now have been functionalized to include thermally conductive offerings, which allow heat dissipation through the encapsulating layer, expanding the use of these materials to new application spaces. Through thermal modeling, we've seen reduction of the component operating temperature for materials with thermal conductivities over a half watt meter K. And finally, Hinko continues to develop new technology to leverage this solution by adding these functional benefits. So with that, I would like to say thank you very much for your time and open the floor up to any questions. So, Graham, MP, back to you.
Thanks, Art. Very interesting presentation. Very, very interesting indeed. Thank you. And attendees, if you are thinking of questions, now is the time to post them. We have 3 questions queued up currently. If you wish to post a question, just use the Q&A button at the bottom of your screen now, and we'll do our very best to answer them for you. At this point, I'm going to hand over the Q&A to the Senior Technical Editor of Electronics Cooling Magazine, MP Divakar. MP, do you want to take it from here?
Yes, thank you. Thank you, Graham. Again, a great a great presentation. I thoroughly enjoyed it. Once again, good morning and good afternoon and good evening to all the attendees. Keep your questions coming. I see a couple already here. Let me start off with the first question from Rick regarding Technomelt. He is wondering if the material can be custom colored, like green or tan or other colors.
Sure, MB, thanks. Rick, so Technomelt materials, the base resin itself is an amber color. We have 2 standard colors, that amber that's offered and also a material that's pigmented black. We do have other custom colors in our current portfolio, that being an orange for actually electronic vehicles, automotive safety requirements, and also a white material that's UV and thermally stable. For custom coloring such as green or tan, this can be done. We do work with a few compounders who have quite a bit of background on this. They do quite a bit of work for us, actually, for our standard products as well. And they've been able to come up with a variety of custom colors, both using a powder pigment and also a liquid colorant as well.
Okay, our next question comes from Tozer. He has an interesting application. He's wondering if he can apply this material, some variant of it, for improving the contact resistance between two metal surfaces. For example, what you see in the case of a connector, I would imagine he's talking about InfiniBand or QSFP type connectors, that the connector mates into a cage, and he is wondering if he can improve the contact resistance so that way you can conduct more heat to the cage, the surrounding medium where the connector mates with.
I think I need to understand the application in more details, but I would say from our background with our thermal management materials, I understand the interfacial contact resistance is something to always be concerned with. In this application or this material set, I don't see it as being dispensed or injected in between two things, but if it was encapsulating around them, for instance, you would probably see more intimate contact with the surfaces itself, allow that bulk conductivity to really take over and not be as limited with the interfacial contact resistance.
I see. I have I have a couple of questions from my side.
Sure.
What is the typical shrinkage percentage of this material?
The material does shrink, and it's up to 5% during the process, or actually I think it's even a little bit more than that. But the way that the equipment works, it continues to apply pressure during that cooling cycle where the material shrinks and allows the backfilling to manage the stress through that. So even though it shrinks during its cooling or during its process, it really doesn't have much effect or impact because of the way that the equipment itself handles the application.
Oh, I see. So does that effectively answer any DLAM, with the board, for example, solder mask, or even, maybe the CTE mismatch with the components on the board? So are those things mitigated with what you just described?
So if you're thinking about CTE mismatch between two very hard things, so for instance, an epoxy potting material or something like that, you start to look at the CTE mismatch itself to measure how much stress is produced, and then the modules of the material to see how well that material can manage the stress, either before cracking a component or cracking itself or delamming, as you mentioned before.
Okay.
This material is slightly different given that it's a thermoplastic. So yeah, the shrinkage allows for the material to mold very intimately around the board and create an adhesion there. But since it has a different stress profile where it doesn't have you're not going through its TG, it's not a thermal set, the way that the stress is managed via the material, it's a little bit more flexible. So it absorbs that stress a little bit more without seeing the fatigue in the adhesion itself.
Our next question comes from Thomas. He's asking whether we need a thicker minimum wall thickness, molded wall thickness for materials like Technomelt. So
the thermally conductive material versus the standard material, no, we use the same mold sets that we've traditionally used. So any mold set that we've had out there, the only change that we've seen a few customers make is adding in inserts to allow for more durability on the actual molded part. So the mold set itself is aluminum. They might put an insert in that's stainless steel to prevent any further wear. But from changing the actual wall dimensions, I haven't seen that as an issue. Perhaps if you're looking at something more novel like a 3D printed mold set where it's a different material, you may have to make considerations like that, but some mold flow analysis should be able to tell you whether that's required or not.
I see. We have one more question from Rick. He's wondering, that example you show with the handle-like feature, it's got the skyline. How did you do the mold for that? Was there a slider, for the undercut?
The mold set itself is two parts, so it's just the way that the mold was designed. The part was placed in with a overhang on the mold set itself. The second mold set comes over the top of the handle, and the gap then is filled with the material, creating that nice skylined part.
Okay. I have next from Herb Reiter. Hello again, Herb, a colleague of mine in the Silicon Valley. He's wondering for the 5G wireless technology, especially when you're driving up frequencies, the baseband up to 70 gigahertz. With the loss characteristics you need, can this material be used in such high frequency applications?
So I don't have an answer for that right now, given the parameters that you put forward at 70 gigahertz, but we have been doing quite a bit of testing internally for EMI shielding, for instance, to understand the performance of these materials. We are characterizing these to see what their insertion loss is relative to different operating frequencies. So I'm more than happy to connect you with the people internally that are doing that test, but for this encapsulation material, we don't do a tremendous amount of insertion loss measurement unless it's on an application basis.
Okay. Another question from James. He's wanting to know the dielectric properties, typical dielectric properties of Technomelt. I would imagine the dielectric constant and loss tangent.
Sure. So I'm trying to scroll back to see if it's available in any of the slides. We do measure dielectric strength, obviously, and dielectric constant dissipation factor for all of the materials. The unfilled resins meet a very, I'd say, traditional level of dielectric strength or dielectric properties that we would want to see. Additionally, though, the thermally conductive material is measuring much better given the filler addition to it. And I can give you more specifics offline. I don't have the data next to me at this point.
Okay. Yeah, this is something I suppose we can follow up, with later Q&A through email. One more. I think that's been answered. That's just about what I have so far. If there's any more audience questions, we can hang around and talk about a few other things. Let me ask one of mine. Is this material somewhat amenable to 3D printing?
This material has actually been used in 3D printing applications with various consortiums in Europe, for instance. We've looked at the thermally conductive material to see if it would work with 3D printing technology, and we're still investigating that at present. We've also had some other concepts for functional materials that seem to be interesting as well to the 3D printing market, and especially creating 3D printed circuits themselves. So it's undefined at this point, but it's an area of interest for Hinkle as a corporation.
Okay. We're almost at the end of the presentation and Q&A. Let me pose a question as the closing thought. How do you see this being implemented in a manufacturing line? So imagine if it's an SMT line with assemblies, circuit board assemblies. How does this fit into a flow in a manufacturing scenario?
Very similar to how you would see a potting or other traditional encapsulation process set up in a line. So parts typically go through an SMT process. The parts are, components are mounted on the board, possibly go through a functional test to make sure that solder application, there was no issues with BGAs, for instance, or something of that nature. Once those components are marked for ready to be final assembly, they typically go to the encapsulation side of things. And in this case, they would go to a low-pressure molding line, where the parts would be inserted, molded, and then taken out the other side for any kind of final connection or assembly or test that would need to be done. So it's a very inline type of a process. In this case, depending on the size of the component, you can mold multiple parts at one time if need be to increase your throughput per step, but very similar to how you would see any traditional encapsulation process take place.
Okay, great. I think with that, we have to wrap up. Again, it was an excellent presentation, lots of useful information. From my side, personally, I'm looking forward to your future generations with higher thermal conductivity. Again, thanks to the audience and the presenters. So we have to wrap up, and we have another one starting in 15 minutes. And have a good day all. Thank you. Bye.
Appreciate it.